Tim Clayton. I think I would stand here as a forensic mathematician, and what I have to say today is joint work with my PhD student Timber Kerkvliet. I took the challenge of the organizers very seriously. The title of this week, this workshop, was to what extent, what kind of questions can we answer using probabilistic or statistical methods. And to some extent, the answer to this question, of course, also depends on the machinery, the mathematical machinery that we have at our disposal. I think that some of the problems that have been discussed here over the last few days, for instance, problems with the prior probability, we've heard a lot about prior probability, I think that some of these problems, or even most of these problems, are symptoms. They're symptoms of the fact, I think, of my conviction, that the classical probabilities are not so suitable to deal with epistemic probability, which is really the kind of probability that we encounter when we are in the courtroom. I will mention a few of these problems, and I'll have an alternative.
You can define better what you mean by classical probability.
Classical probability, I simply mean probability based on the axioms of Kolmogorov.
But this is not a probability, this is nothing, this is just a mathematical...
No, this is, I mean a mathematical definition of classical mathematical probability, right? That's what I mean.
Okay.
That's, okay, yeah. So, I simply mean probabilities in which things are additive. The probability of A plus the probability of B is the probability of the union of A and B when A and B are disjoint, right? Okay. So, I believe that what is called a belief function is an improvement over using probabilities, and belief functions are just extensions, they are just generalizations. I will spend a few minutes to just simply technically explain to you what a belief function is. And then I move forward very quickly to show that these belief functions can be set up and can actually be used in a forensic context, and I will show you how to use it in a very classical situation, the classical island problem. Right? But then of course the question comes up, oh nice, these belief functions, why would belief functions have more to do with epistemic probability than classical probability? And I will spend a few minutes on the philosophical backup of that, and if I have more time, I will actually give you some more examples of how belief functions can be used and sometimes can also be computed. So, epistemic probability means that we deal with, not with facts directly, but we deal with our beliefs in these facts. In the philosophical literature, very often this is called degrees of belief. We deal with degrees of belief, and some authors use the term provability in this sense, which I sort of like in this context because it is provability really in the legal sense. Now it is clear that if we concentrate on the word provability, just for concreteness and for simplicity, it is clear perhaps that provability does not necessarily satisfy the classical rules of probability. For instance, if I take some event, some hypothesis, it is very well possible that I'm not able to prove that E occurs, this event, but at the same time I'm not able to prove that its complement, the negation of this hypothesis, occurs. Right? So it's not necessarily the case that provability adds up to 1, so to speak. Right? Another problem that you encounter when you do classical probability is the problem, and we've seen this before, that you have with the prior. One of the speakers yesterday mentioned the fact that, at some point perhaps you would like to assign a prior of 0 to something, but that's of course impossible. Well, it is possible, but if you apply a prior of 0, no matter what you do with Bayes' rule, 0 remains 0 and 1 remains 1. The nice thing about belief function is that in fact you can in a very meaningful way apply a 0 prior probability if that's what really corresponds to your knowledge. And I will explain this.
Classical as well.
Classical.
Shooting straw men is not very interesting.
I'm sorry?
Shooting straw men is not very interesting.
I don't know what you mean by that. But let's continue, and we will see in a moment what I mean by this. Right? We will see in a moment. I will give you a concrete example. This island problem example that I mentioned before, that you can really treat in the let me call it the usual way, with a certain prior probabilities on the guilt of certain people in the island, right? And I offer an alternative, right? And you can judge for yourself later on whether or not you like this alternative. Okay, so we shall do that. Okay, so, but before I can give you this example, I have to tell you what the belief function actually is. We know what the probability is. If we have, let's say everything is finite, let's say we have a finite space of possibilities, a finite space of outcomes, a probability distribution simply assigns numbers to these outcomes in such a way that they sum up positive numbers in such a way that they add up to 1. Right? Now, a belief function, it's not my invention, it's what invented in the 1970s, I'll come back to that a little later. A belief function is a slightly different concept. It runs as follows. Instead of a probability distribution on the elements of my outcome omega, or my outcome set, I take a probability distribution on the subsets of omega. So you take one level higher. And this M is a classical probability distribution, an ordinary probability distribution on the subsets of omega. And as a result, if you sum over all subsets of omega, M adds up to 1. That's what it means. So that's my basic probability assignment M. And I'll give you an example. I know this is a little technical. I hope you forgive me for a couple of minutes. I give you a very concrete forensic example in a few minutes. Right? So that's my basic probability assignment. Now a belief function is defined simply as follows. What is my belief? Abbreviated BEL, belief of some event, some hypothesis A. It is simply the sum over all probabilities M of subsets which imply A. That's the definition. So I give you this probability distribution over the subsets of omega, right? And then a belief in a certain subset is simply defined. I simply define something for you, and of course I have to convince you that this makes sense. But I will try to. And then my belief in my subset A is simply the sum of the probabilities M of all events, all hypotheses that actually imply my event A of interest. Right?
Could you substitute them with the P?
Well, I could do that, but this is just classical notation for this basic. I simply follow. If you wish, you could write a P for that, but people simply write M for that. And I want you to notice that this actually extends the classical probability in the sense that every probability distribution is also a belief function. If my M concentrate on singletons, right, then of course my belief function, is just an ordinary probability distribution. So I make the concept of probability a little more flexible by doing this. I allow for more possibilities.
1 minute.
Yeah.
Your M is given as a probability distribution of the subset.
That's correct.
Therefore, you cannot confine M to singletons.
Of course I can. A singleton, the subset which contains of 1 point. That's a subset.
Yeah, but then there are
You
other
couldn't give
subsets.
0.
Of course. Of course, they all get 0. If M only gives positive
But then
probability
If
to
all
single,
the other subsets get 0,
yes.
then the probability is concentrated on that one subset.
No. If every singleton gets a positive, if some singletons get a positive measure, and all other subsets get 0 measure, then in fact my belief function is going to be an ordinary probability distribution. Really, you can think of it. It's true.
The point is that M is not a probability distribution of omega, but
Remember that M is M.
Sorry, I'm not agreeing with this at all. You have a set of singletons which have positive probability. Therefore, all sets consisting of elements of those singletons are
Suppose-
sets which have probability.
Suppose omega is 1, 2, right? Suppose my M of 1 is 1/3, and suppose my M of 2 is 2/3, right? This is a perfect probability distribution on two subsets.
Yeah. What I would like is 1, 2, and 3.
Fine. This then is fine. Then the M of 3 apparently must be 0. That's it.
That is one very special probability distribution.
This is a distribution.
Here's no time.
But now I suppose I put 1/3 on 1, 2, and 3.
That's fine. That's also fine.
Then 1, union 2 has probability 1.
No, it's not. Does not. It does not. It does not. Okay, can we discuss this a little later? Because it will take all my time now, and I don't think I want to do that.
The union of 1 and 2
No.
is a subset
No.
of omega.
No.
Yes, it is.
It's the probability measure. The probability measure is one layer higher than the element of omega. It's a probability distribution on the subsets.
I think we need to come back to this.
Yeah, we come back later. So okay. So I come later. So here's an example. So for instance, one can take, let's say, the measure of a certain set A to be 0.1, the measure of its complement also 0.1, and the measure of the full space omega is a subset of itself. I take that 0.8. That's allowed. Adds up to 1. And now you see that my belief in a set B, which contains A, but is not equal to omega, is simply 0.1, because there's only one set with positive M measure that implies B, and that's A itself. And the belief of the complement of B is 0. So you see, the belief of B and the belief of B complement can both be small. That's possible now. Just as a technical fact, I offer this to you. What it means, we talk about it a little later. And this second example is also quite interesting. What you can do is you can put all the mass on the full space. That's allowed. So the M of the full space is 1. That means that every strict subset of omega now has belief 0. Right? Because there's no set with positive M measure that implies it. So this can be used as a prior, say, in an island situation with 10 participants. I take a bit of water. Can be used in an island situation with 10 participants. And suppose I know for sure that one of the inhabitants of the island is the criminal, but I have no further information, then this could be my prior belief function. It's rather unusual. I know this is rather unusual. It has taken me a lot of time to get used to it, and so it's kind of difficult to explain. No, but let's see. So, of course, when you have probabilities, we do conditioning. We do conditioning all the time. Bayes' rule is saying the probability of a certain event given a certain hypothesis. And this is no different in the world of belief functions. Right? So I have to give a rule how conditioning works. And the rule is very simple and very straightforward, namely as follows. Remember this basic probability assignment M, which was that was the mass assigned to A. If I condition on an hypothesis H, I simply take that mass that was assigned to A and I assign it to the intersection of H and A, and then you normalize to keep things 1, which is very, very similar to what you do in classical probability calculus. And of course, when you check it, when my original belief function was a probability distribution, then of course this type of conditioning coincides with classical conditioning. Right? Okay, so doing this leads to a new basic probability assignment, and therefore also a new belief function, and they are called belief of H conditioned on H, and my basic belief assignment conditioned on H. So that means I have a machinery now, a very simple machinery, that tells me how I should take certain events into account, how I should compute beliefs conditioned on certain events. I can do this now. Right? And still this is abstract, so here's my one formula that I find very important. And I'm going to explain you what this formula says. So this is an example of belief function in action, and maybe we should see it here as a proof of principle. It can work. It can work. Let me explain you what the situation is. The situation is, I have a population on an island, and for some reason, the number of people on this island is n plus 1, for some reason, okay? Now suppose there is some crime committed on the island. It's a very ideal theoretical situation, right? So I know that there are many problems with this, but this is the classical island problem. A DNA profile, call it gamma, and the DNA profile has a certain population frequency. I know there are problems with that, but let's ignore that, which is P. Now there's a number of things that happen. So there must be a criminal on the island because the crime must have been committed by somebody from this population. This criminal is called C. In a moment we will select a person from the island and we call that selected person S. We choose it at random. And we have, of course, the indicators. We know or we can think about the probabilistic experiment of for each person on the island, giving each of them this characteristic, this profile gamma or not. And these are given by these little y's. So y1 up to yn plus 1 are just 0, 1 variables. A 0 means the person in question does not have this profile, and a 1 means he does. Okay, that's the situation. So now I select a person from the island, right? Okay, and now I want to think about what do I actually know? What do I know from this situation? Classically, what you would do is you would have to impose a prior on the question, on the population, from who's the criminal or not. And you can take a uniform prior. I will do this in a moment also. But here I do something different, and this is maybe the key to what I want to tell you. I do something different here. So here's my prior belief function. And what does it say? It says the following. It says the following. The probability, because M is a probability, right? The probability that a certain person X was selected, right? That a certain person X was selected, and that the profiles of all the people in the island was a certain sequence of zeros and ones, right? This probability I can compute, right? But notice that I do something different with C. I don't say here my prior conviction or my prior probability that person 0 or 1 is the criminal is 1 over n plus 1. I don't do that. I say nothing about the criminal, absolutely nothing other than that this criminal belongs to the island population. That's all I say, right? So this means effectively I have made no prior assumption on my C other than that it belongs to the island population. And I can write this down. This 1 over n plus 1 simply comes from the fact that I do choose my S, my selected person, I do choose it randomly. So the probability that a certain person is selected really is 1 over n plus 1. And I assume independence, and this gives the probability that my profiles actually are as they appear to be, right? That they are y1 up to yn plus 1. Had I also wanted to incorporate prior knowledge about C, I could have done that. I could have done that also in this machinery. As I say, it extends classical probability. So I can also do classical things, and the only thing that would change then would be that instead of C and X, I would write here C is equal to some Y, right? And I would have added, I would have multiplied by another term, another factor, 1 over n plus 1. That would correspond to a uniform prior over my C, for my C. But I don't do this here, I don't need to do this. Because this is a probability measure on subsets of my outcome space. It's a perfectly fine probability measure, of course, because it is, because I described it as a probabilistic experiment. And I can do that, right? And what happens then is the following. You can now do the calculus that I explained very, very briefly to you. I know it was very brief. You can explain the calculus, you can do the calculus, and you can condition on the event that my S, some certain S was chosen, and that the criminal C and my chosen F happen to have the same profile, gamma. That's the information I have, and then I can compute. Of course, one can do that, you can do the computations, and you can show then that the conditional belief under this condition, this event which I denoted HS here, the conditional belief that C is indeed my criminal turns out to be, in this particular simple case, to be a very simple formula, 1 minus p to the power n. And it is nice to compare this to the answer that you would get when you do uniform priors over C, right? There might be circumstances where this is what you want to do, right? If you take uniform priors over C, and I explained on the previous slide that this machinery simply allows for that. I simply extend things. I do not dismiss classical probability. I try to extend it a little bit. So in the classical case with a uniform prior, and this is classical, right? David Boulding did this already a long time ago, and many people actually, well, some people did wrong calculations, but that's okay. This is the answer, right? So this is what you would get classically. And you can compare these numbers, and it should, at least intuitively, I think intuitively, it should not come as a surprise that the belief answer is smaller than the answer with uniform priors, which in some sense makes sense, at least in my mind, because I start with less incriminating evidence or incriminating numbers, right? Because I assigned 0 belief to each individual. Right? I assigned belief of 1 to the full group, but 0 belief to each individual, right? And that's perfectly fine in our setup, and it leads to different and therefore, in many cases like this, smaller numbers. Right? So this is a first forensic example which tells me that I actually can apply this theory in certain situations. Right? That's the first, I would call this a baby example of applying belief functions in a forensic context. Okay. Now, having said that, it is obvious that there are important philosophical issues to deal with. I mean, why? Why do I think that classical probability is not so suitable? Well, because I think that, as I said before, that certain facts about epistemic probability are not well captured by classical axioms. But then, of course, this begs the question: okay, so now I have to convince myself and anybody else that, in fact, belief functions do have this property, that they somehow reflect or better reflect the idea of epistemic probability. Okay, so what can I say about that? So that's number 2. I will come back to number 1 in a second. It is possible to set up a philosophical framework for belief functions very similar to the Dutch book argument why probability distributions are what they are. Right? You can actually characterize probability distributions in terms of how much money you are willing to bet on a certain event given certain consistency requirements. Right? These characterize probability distributions. Right? Now, if you look at that whole machinery, that whole process, you can see in that process where actually belief functions come in, where epistemic probability comes in, and the crucial difference turns out to be the fact or the idea that the price that I want to buy a certain bet for is not necessarily the same as the price that I want to sell a bet for. These things can be very different for good reasons. So it is possible to really set it up from scratch and then arrive necessarily at belief functions. It simply turns out that belief functions are the ones that satisfy these criteria, which gives the same philosophical backup to belief functions as the Dutch book argument serves as a philosophical backup for classical probability distributions. So that's all possible. We've written this down in a philosophical paper, which you can have a look at, which actually gives me a philosophical backup. But there's another problem. As I told you, I'm not the one that invented belief functions. This honor goes to Glenn Shaver in the 70s. In the 70s, there were a number of attempts to deal with the problem that many people noticed that epistemic probability did not really satisfy axioms of classical probability theory. And among these people were Cohen, who wrote a very interesting book, Proof and Provability, something like that, and there was Glenn Shaver, who came up with his belief functions. But belief functions never made it, really. Of course, they made it in certain communities, and there are still books written on it, but mainstream mathematics, mainstream probability is not associated. You don't see belief functions there. And I think I know why. The fact is that Glenn Shaver not only introduced belief functions, but he also introduced some sort of belief function calculus comparable to classical probability calculus that we all know. And this calculus was unacceptable to many, including for me. And people thought, well, this calculus we cannot work with, it doesn't make sense. And if you come to think of it, it doesn't really make sense, but the good news is that you can do without. So you can set up a calculus that avoids this Dempster's rule of combination of belief functions. You don't need it. Right? So the other obstruction was that there was no behavioral interpretation of belief functions, but that has been taken care of by number 2. There is really a behavioral interpretation which makes belief functions extremely suitable for quantifying degrees of belief or provability, which is the kind of probability that we deal with when we are in the courtroom. So that's the philosophical backup. I'm not going to say a lot more about that because I want to spend my last 2 minutes or so on 2 more formulas. I'm just telling you that we have done that. So this is another example, another island problem. There are many island problems. This is the one with search. So here's a problem that you have your island, the same situation as before, and you start to look for your suspect, and you look until you find somebody that has the right DNA profile that you found at the scene of the crime. Now, of course, this is a different procedure, so you get different answers, and there was, in fact, David Balding has written hilariously about that. You see many different answers in the literature, and the length of the search is not reported, because if you do that, you even get again different answers. Now, in our beliefs, you can do this. So you can set this up in the belief theory. You get this answer that I quoted here, and in this case, the answer is a little more complicated. This is the classical answer, where you start with uniform priors, and in this case, it's rather beautiful. I mean, of course, I'm a mathematician. I like the aesthetic beauty of mathematics also. The one is the harmonic mean, and the other is the geometric mean. And we know this just happens to be the case. And we know that harmonic means are smaller than geometric means, so we can immediately that indeed in this case as well, belief functions gives a smaller answer than the classical answer, which I think makes sense. Right? So this is another example where we can do the computations. And there's a last example, which I think is quite important, because this has been discussed before here in this lecture room yesterday, that when you do parental identification procedures, I mean, where do you start? So you have this putative father. So what's my prior that this guy actually is the father? So that's a difficult question that I don't know how to answer in the classical situation, but now I sort of can. The only thing I need to know, and I don't think you can get around that, really, you need some upper bound for the number of possible fathers. You don't need to know them, but you need an upper bound. And I think basic biology tells me that this number should not be extremely high, right? I mean, typically women didn't have sex with 5,000 people, right? So there's a number there. So if you do that, so this formula, this is just a baby case, because the computations in these situations are not so easy. So this is a simple case where you take one locus, you know which paternal allele was missing, and the putative father that we have here has one such allele, which is different, of course, from the situation that he has 2. You can set everything up. You can do the basic probability assignment, of course, different now, but you can do this in this situation. You can do the conditioning, you can do the computations. I don't say it's simple, but you can do it, and you get this answer here, that the belief that this particular guy is the father is this beautiful number, where P0 and P1 are the probabilities that the random chosen person has 0 or 1 alleles of that type. And I again ignore all population problems with that. And there's also, of course, a classical answer, which is given by that, assuming uniform price. Again, it's bigger. That's another thing. And you can arrive at this classical answer again with this machinery by just changing your original basic belief assignment. So the conclusion is that there is a philosophical backup of this object of belief functions. And I genuinely believe that these belief functions are the right objects to deal with epistemic probability. And there's a proof of principle in forensic settings. It works, and in many cases it can be computed. And belief functions therefore solve some of the problems that we have encountered here. Right? It's really possible now, to let your prior correspond to your actual knowledge. A 0 prior on the individual basis is possible for all people involved. This is now possible, which I think is a significant step, I think. Right? So of course, I think we are at the beginning of this whole development. Of course, we are in the process of working out a lot more complicated examples. This is not so easy, actually. Another thing that I'm doing right now, that I'm developing right now, is a theory of Bayesian networks. I'm not sure you have to call it a Bayesian network, but maybe you know what I mean. It's a network structure where certain dependencies arise, and you want to send up a belief function for the full network. Because you don't have basic room at your disposal, of course, that doesn't exist anymore, but you have an algorithmic version of that. I don't have formulas, but I can still do it. Right? And of course, I'm a mathematician. As a mathematician, as you know, I just want to develop the mathematical theory and want to develop belief functions not only in finite spaces, but in infinite spaces as well. And this is a very serious business. Right? So this is difficult. And of course, one of my projects is what I'm doing right now. I try to convince people that this is indeed an interesting object to look at. I hope you enjoyed the talk. Thank you very much.
Maybe take one or two questions now, and then we discuss it. So Phil, do you want to?
Well, you're selling your theory as a generalization of ordinary probability theory, but there's also a generalization of belief function theory, which is imprecise probability theory.
Yeah.
And there's a whole enterprise, enormous school of people dealing with interval value probabilities, which don't necessarily have any connection with belief functions, but they do correspond to your idea of different buying and selling prices. So how do you specify that you're going to use the particular form that you do?
The reason that I want to use this particular form that I do is based on my philosophical backup. What we do is we set up a number of, we think are sort of well, of course you can question anything, but some natural starting points, and then we develop the theory, and we simply arrive at belief functions of this form. This is our backup. It may or may not be convincing, but this is an answer to your question. Yeah.
Okay, I think maybe we'll take a break now because we've got plenty of time for discussion. So thank Ronald again for a provocative talk.
Yeah.